Okay, now we talk about principle of superposition. What is superposition? So this theorem states that if we have many sources in the circuit, we can solve the source one by one, and we will get the more simple circuit to solve. For example, if we have VB1 and VB2 of this circuit, we can solve circuit A with only VB1 to solve for IB1. And then we solve only the circuit, only VB2. And then IB2 will obtain, and I will be IB1 plus IB2. Okay. So if you have voltage source, you substitute the voltage source as zero voltage. What is zero voltage? What is zero voltage? Short circuit, right? So the voltage source will be substituted by short circuit, and the current source you will substitute by zero current. What is zero current? Open circuit, like this, right? And then you can solve the circuit, and after that you sum the solution together. Okay, we call superposition theorem. Okay. For example, if we have the circuit with Vs and Is, so we solve the circuit with Vs equal to 0, like this. For example, we solve for I of R2, like this. We can solve for I of R2, right? This circuit is not difficult. Okay, with this short circuit. Then again, we set Is to 0. We can solve R2, okay? We can solve this circuit for R2, right? This circuit is more simple. So this is I of R2 with Vs set to 0. And this circuit of R2 with Is set to 0, right? And for overall of I of R2, this will be I of R2 equal to I R2 when Vs set to 0 plus I R2 when Is set to 0. Okay? So to solve this circuit, we can solve these two circuits instead. So which one you choose? You choose to solve these two circuits, or you choose to solve this one single circuit, which are better? Which is better? To solve this circuit and this circuit, to solve two circuits, two easy circuits, and one complex circuit to solve for I R2. Okay? Right? So when you have both voltage source, current source, maybe nodal analysis become difficult. Mesh analysis also difficult, right? So you think about superposition theory, right? When you have different kind of source, it's very useful, right? To solve one by one. Okay? Really funny, right? Solving circuit. Right. I didn't solve the circuit for a long time, right? If I would not teach this class, right? Okay. For example, we have this circuit. We know Vs, Is, and R. Okay, so for I2, yeah, right? We need to solve for I2. So this is mesh. Okay, but we don't need to do mesh current. So first we saw the circuit with IS 0, right? IS is 0. And then we saw when VS is 0, right? Yeah. We saw this I2 and this I2, and this is I2 when IS is 0, and it's I2 when VS is 0, just like this, and we sum together I2 when IS 0 and I2 when VS 0, right? This is not difficult, and this is not difficult, right? Okay. Then how about this circuit? So determine the voltage across resistor R, VR. Okay, determine VR. When we know everything in the circuit. So in this case, similarly, we saw the circuit when VG is 0. VG is 0, right? And then we saw the circuit when IB is 0. Then we get VR. In this case, is VR when VG is 0. And this is VR when IB is 0. So this circuit is not difficult to solve for VR, right? Is that the correct? Can you solve for VR of this circuit? You just get the equivalent that you can sum parallel of the resistor right together, and how much the voltage across, right? Okay, not difficult. And in this case, you can solve for VR also, right? You can use this in parallel circuit, and it's in series form, right? So VR of this circuit. Okay, after that, the VR will be equal to these two values together, right? The VR here. VR is VR when VG is 0 plus VR when IB is 0, right? You need to solve this and solve this circuit, these two circuits, instead of one single but complex circuit. Okay? Not so difficult, but you need to do practice, right? Yeah. Many times that when we sit in the class and we feel that we understand everything, but when we go back, start doing homework, we know that, oh, we don't understand, right? Okay, so in this example, we solve for VR here, right? VR, no, in this case, they said we are in this circuit as we are with I, right? We are with only current source. You see, I write down we are when G is 0 in this case. But we are with only current source here. We are is only current source, right? To solve for VR, they take KCL this node, right? And minus IB. Minus IB plus VR by RB plus VR by RG plus VR by R is 0. So we can get VR here, right? We can get VR at 1.38 volt. Right? Check this. Then for this circuit, you take K, apply KCL also, right? This is VR. This is VR. Then the current flow here, VR by RB. This is VR minus VG, right? VR minus VG by RG. Yeah. this current is VR minus VG divided by RG, right? This current VR divided by R. Then we substitute the known value, we get VR in this case equal to 4.61. Then VR would be these two values summed together is 5.99. Okay? If you solve this circuit directly, you will get VR at 5.99. Right? And then for this circuit, you get VR at 1.38. And in this case, you get 4.61. Okay? This is superposition theorem, right? Okay. Then we can further apply this theorem into the two-port network. So in every complex circuit, we can simplify into two-port network like this V1 and I1. So if we have network, in this case, we may have the complex network. But this network, if the voltage and current of this network will be same as our two-port network. One port is mean two terminal, right? In this case, it means a two-terminal network, right? Into one-port network here, or two-terminal network. Okay. And V and I of this network will represent this complex system. Okay. So we can simplify the circuit into two forms called Thevenin theorem and Norton theorem. Okay. It means that if we have any complex circuit, and we connect, if we have some device connect to the terminal. For example, we have one source or one circuit. If we connect something to this circuit, inside this circuit may be very complex, but we can represent this circuit into one single source and one resistor. Okay? How to do that? If I connect the device into A and B, and then the voltage and current flow. The voltage and current flow from this circuit is V and I, and is equal to this circuit. It's similar to I connect to this circuit. Okay, so if I connect one device into this circuit, and I will get, for example, 3 ampere and 5 volt. If I find out one circuit with very simple circuit, and when I connect the device into its terminal, I also get 3 ampere and 5 volt. We call this circuit as equivalent circuit. Okay, it means that equivalent circuit. Okay, so the complex circuit, we can get equivalent circuit. Okay, like this. If I write out this circuit in equivalent form, usually one single source and one resistor. Equivalent and V equivalent like this, and V and I. It means that when I connect any device to this terminal, to this port, I will get the same characteristic with I connect to this circuit. Okay. Right. For example, if I connect 3 ohm here, I will get volt and current similar to I connect 3 ohm here, right? So it's very convenient to transform this complex circuit into one single source and one resistor. Okay, we call equivalent circuit. This is equivalent circuit, right? Okay, so how to get the equivalent circuit of the complex circuit? So we can get two forms of equivalent circuit with the voltage and resistance. So we call this is Thevenin equivalent, right? Thevenin equivalent circuit. Or we can write out into current source with parallel resistance. We call Norton equivalent circuit. Okay, we have Thevenin and Norton, and we can transform Thevenin and Norton. Okay. Okay, how to determine the Norton or Thevenin equivalent? Okay. First, we need to find out what is VT and RT, or IN and RN. Okay. So to solve for VT, this is the voltage of this terminal. For example, this circuit that we would like to solve for Norton equivalent. So the voltage is A and B, is VA and B without the loss. And for this is VT is VAB, right? Open circuit. And for the Thevenin, we can solve by remove all source in the system, right? For the voltage source, we short circuit. Similarly, for voltage source, we make it short, and for current source, we make it open as open circuit, right? So in this case, we short circuit, and we solve for resistance of this circuit, right? Here we can get the resistance is R1, R2 in parallel and plus R3. So this will be R3 plus R1 in parallel with R2 as Thevenin. Okay. For this example, right, to find out the Thevenin equivalent, right? So first we find out the voltage between AB is will be V Thevenin without RL. Okay. And then we solve for R Thevenin by removing the source, right? The current will be what? Open circuit, right? Open circuit. So without this current source, we solve for resistance or resistance, right? So in this case, we know R1, R2, R3, R4, R5 as 20, 20, 10, and then 20 and 10, right? So in parallel it will be 10. 10 plus 10 is 20, in parallel is 10. 10 plus 10 is 20, right here. Okay. So R is 20. So how about V Thevenin? V Thevenin is the voltage of this circuit without RL. or they just would like us to find out RL, right? VT later, okay? Okay, so in this case, to find out RL, R Thevenin also, no RT, sorry, RT. In this case, what is RT? This voltage become short, right? And this current become open, right? Here is the curve. And then we can get for RT. Okay. So the Thevenin and Norton equivalent resistance are the same quantity, right? If we get R Thevenin, we can use this for R Norton. This is same value. Okay. So how to compute the Thevenin voltage? The Thevenin voltage is a voltage without RL, right? When we remove RL, okay. We just solve for Thevenin. For this example, for this example, if we would like to solve for Thevenin equivalent, is VAB, right? Right? We can solve for VAB. Right? This is V, this is V. So how to solve for VAB? Any method. Okay. So in this case, if we take node analysis, okay, this is V, and this is VA, and this is V, right? So the unknown is V and VA. Right? Or for example, this is V1 and this is V2. You can solve in this form, right? And then V2 become VA. Right? So for this current, V minus V here. This is the current flow here, right? V capital V minus V divided by R1, right? V here is 12 volt, right? And then minus V divided by R2, and then minus V minus VA divided by R3, right here. We get this equation. Okay. We substitute, we get this form. Okay. R3 is 10, right? Yeah. Now we need another equation, right? In fact. So how about this equation? V minus VA, right? V minus VA divided, oh, this is the second equation, sorry. V minus VA divided by R3, and then minus VA divided by R4, right? Yeah. Then we substitute the known value, we get this and this. And we solve two equation, two unknown, right? Then we get VA. So this is V Thevenin. So this circuit can be represented by Thevenin circuit like this. This is 7.059 volt, and this is R Thevenin. To solve for R Thevenin, you short this part and you solve for total resistance, right? You will get R Thevenin. So this circuit can be represented by this circuit. Okay, this circuit can be represented by this circuit. Equivalent circuit. To get the Norton equivalent, you transform this into current source with the in parallel of this is RT also. Okay, and this is would be 7.059 divided by RT for Norton current. Okay. let's see this example. We have V at 24 ohm, I is 3 amp, and R1 4 ohm, R2 12, R3 is 6 ohm, right? But we would like to use R3 as RL, right? And then find out the Thevenin equivalent of this part. Then we remove R3. And solving for R Thevenin, what is R Thevenin? R Thevenin is the circuit when current source is open, right? Current source is open and voltage source is short. Then we get this circuit, right? R1 and I2 in parallel is 3 ohm. Okay, 4 and 12 in parallel we get 3 ohm, right? 3 ohm, yeah. So how to get the Thevenin voltage? Thevenin voltage is the voltage between A and B. A and B here, right? Here. We solve for VA. Okay. Any method. In this case, if we take KCL, we have one node, right? So what is this current? V minus VA divided by R, right? V minus VA divided by R, right? The current here. And this current here, I. Right? I. And this current flowing this direction, VA divided by R2. Right? And we know V, how much? 24. I is 3. R1 is 4 and R2 is 12. Right? And then we get VA, right? VA is V open circuit, right? This is VA is 27 volt, then this is 27 volt. So we can find out the equivalent circuit of this circuit into one single source and one resistor, right? When we connect 6 ohm here, it will be equivalent to connecting 6 ohm here. Okay, it's equivalent. How to find out equivalent circuit is to solve for RT and VT. VT is V open circuit, right? Just the voltage of the connecting point and the resistance without any source. Okay, resistance without any source, like this. If you solve I from this circuit, it will be equal to solve for I from this circuit. Okay, so if you use this circuit very often, it's more convenient to transform into this circuit, right? Okay, when we connect 6 ohm, sometimes we connect 5 ohm, sometimes we connect 1 ohm, right? You solve from this circuit, but you get the same value, right? So you don't want to solve this circuit really often, right? But this circuit is okay, right? So how many current? So you get 27 divided by 9, right? Like this. Okay, this we call Thevenin equivalent circuit. Okay, and we can also transform Thevenin equivalent into Norton equivalent circuit. Norton equivalent circuit, we will get this equivalent circuit. We call this is Norton equivalent circuit. This is also 3 ohm. And this is 27 divided by 3. How much? 9. By 3 is 9 ampere. This is Norton. When you get Thevenin equivalent circuit, it's very easy to get Norton equivalent circuit. Okay, this is sometimes we call short circuit current. It means if we short this terminal, how much the current flows? If we short this terminal, if we short the Norton circuit, the current will flow. Here, if we short this, it's 27 divided by 3, right? This is a short circuit current, it's 9 amp. So also, similarly, if you connect 6 ohm here, you will get the same solution. Okay? So whichever the equivalent circuit you can use, Norton circuit Okay, or you can transform your circuit into, Thevenin circuit, or you can transform into Norton circuit, right? It's also more simple, right? Than your original circuit. This also one equivalent circuit to this. Okay, we have two types of equivalent circuit, Thevenin and Norton. Okay, if you get Thevenin, you will get Norton very easy. Okay, Norton circuit very easy. Okay, here is how to compute Norton current. You just short circuit at the port right here. Right, you can get ISC as an I Norton, and R Thevenin and R Norton are same, right? Because when you short circuit here, it's similar to short circuit here. Okay. Right, this in this circuit. Okay. Okay, this example, I think I leave this example for you because this example are just similar to the previous one, and in this case, we find out the Norton current, right? Norton current is short circuit current. If you short here, you get Norton current, or you find out Thevenin equivalent first, right? If you find Thevenin, you short it, you will get Norton current, right? In this case, if you short from the original circuit, you will get Norton current also. So I think I leave this equation, this example for you. So source transform is the Thevenin and Norton equivalent, right? I think it's okay. Source transform is maybe convenient when you have like this. If you have Thevenin form, you convert into Norton form. Voltage source in series with resistor can be represented by current source in parallel with resistor, right? This is also you can transform. If your circuit become easier to solve, this will be useful, right? But if you transform and it become more complex, so you don't need to do that, right? Okay, in this case, it may be good to transform, right? All into current source like that, or all into voltage source like that, okay? Okay. This is the experimentation of Thevenin and Norton. This is okay. I think just some experimentation part. Maybe you have done this in the laboratory. Thevenin Norton in your lab, right? No? Not yet, but this topic is there, right? No? You will do this, right? You have to do this, right? Okay, I think that, so maybe. Okay, this is homework 4. Okay. So now we have 4 homework, right? Too many homework. It's good to do a lot of practice with circuit analysis. Okay? Because it's a lot of computation, it's made you get more understanding. And you get the skill when do the examination, right? Okay, any question? Theory Norton, I think you better go back to remind again about the all example that we discussed today. Okay. No question?